Lesson number 5 in chapter 2 is about differentiability, and it's just a way of saying or asking the question, can you take the derivative? Can you take the derivative? So we're going to look at a few cases where you cannot take the derivative, and below here are 3 things that are true. A function is not differentiable, or you cannot take the derivative under the 3 cases. The first one is if the function is discontinuous at some value x equals c. So let's say that at c we have maybe a piecewise function that looks like this, and then at c it goes something like this. Because it's not continuous, you can't take the derivative. Although it should be noted that you can take the derivative from the left-hand side. That would be whatever the slope of that straight line is. And, excuse me, that was from the left side. And from the right-hand side, as you come in and approach that, you can also take the derivative. This is a horizontal line, so the derivative would equal 0, but because it's not continuous, you cannot take the derivative at that spot at c. So another scenario that we'll look at is if you have what's called a cusp or a sharp turn or sharp corner. So you may have something that looks like this, and that's also defined at c in this definition. So right there was equal to c. And likewise, you can take the derivative anywhere along this curve from the left-hand side, and from the right-hand side you can take the derivative anywhere. But because when you get to that sharp corner, it's not a smooth transition, so it never equals a horizontal line there. It just sort of takes that sharp turn, so you can't take the derivative of that. Another example of a sharp corner might be, of course, the absolute value. That would be the upside down absolute value, so might look something like this. Absolute value of, let's try that again. So for example, this one might be f of x is equal to the opposite of the absolute value of x minus 4. And at that spot where, and this would be risen up a few spots. So this function, and that I just drew in red, you can take the derivative to the left of, this would be positive 4. You can take the derivative of that line to the left and to the right of 4, but at 4, because of that sharp corner or that sharp turn, you cannot take the derivative. And the last example is if you have a vertical tangent. So perhaps you've got some sort of curve that's flowing along here, and then it just sort of raises up sharply. So this middle section right here has a vertical tangent, which is of course undefined. So those are the 3 scenarios you need to keep in mind. So with those 3 concepts, let's take a look at the notes here. So the first question says, sketch the graph of 1 over x minus 3, and by visual inspection determine any points at which it is not differentiable. So of course what we're interested in is, when is this function, when does it have any discontinuities, and it looks like when x equals 3, the denominator goes to 0. You can't factor that out. So at x equals 3, you've got yourself an asymptote that goes right here, a vertical one. And when you look at this graph, as you approach it from the left, this thing goes down to negative infinity. And as you approach it on the right hand side, it approaches positive infinity. So it's not differentiable at 3 because it's not continuous right there. And example 2 wants you to sketch the absolute value of x plus 2. So just a little mini review about absolute values. You're interested in when does the inside portion of that equal to 0. So you set x plus 2 to 0, and of course x equals a negative 2 is where the absolute value function comes together. And this one would look something like this. So it is not differentiable at x equals a negative 2 because it has a cusp, and remember that's just nothing more than a sharp corner or sharp turn at negative 2. But everywhere else it's differentiable. So it's differentiable on the left hand side, it's differentiable on the right hand side as we come down, but at that spot at x equals negative 2 it is not differentiable. Alright, and the next one's kind of interesting. Let's take a look at that on the calculator. And I've already put this in. So let's see if we can't move this over a little bit. Alright, having a little bit of difficulty. There we go. So at this value here, let's go ahead and put it in the calculator. 4 times x to the 1/3 power, and if we look at the graph, we can see that it sort of has a spot of vertical tangency. Let me see if I can copy that. Okay. Whoop. Okay, let's see here. Maybe right about there would be fine. Or you can draw on it a little bit. You can see that this graph comes along here. From the right it's coming in this direction. And right there around 0, it appears to just really blow up. Now, it is continuous there. It's continuous there, but it also has a, let me erase that and put a different color. It has a vertical tangent line there, so it just sort of blows up a little bit and then it continues on. So once again, this thing is it's continuous. It's differentiable to the left. It's also differentiable when you jump back over on the curve on this side, but where that spot of vertical tangency is, right there in the middle, it's not differentiable. Alright, let's take a look at the very last example on our notes here, and we'll see a piecewise function. And let's look at the conditions here. It says to determine if the function is differentiable at x equals 2. It's really not necessary to draw the graph, but it's also helpful sometimes to draw the graph. So where's the dividing line? It looks like it's at x equals 2. So when I'm greater than 2, I follow the line 2x. When I'm less than 2, which I'll do in green, when it's less than 2, we follow x squared. So let's first see if it's continuous just by using algebraic techniques, just plugging it in. So the green function, x squared at 2 would equal what? 2 squared, 4. And on the red one, 2x, plugging in 2, I get 4. So this graph is continuous there. So we don't fail the differentiability on the first test, but we still have to look at the other two cases. So let's go ahead and look at this graphically, and then we'll review what happens when we use the limit definition of the derivative. Okay, so let's graph when it's greater than 2. So we're going to have to go up our graph 1, 2, 3, 4, and it's greater than 2. We're going to have a open circle here, and we have a rise over run of 2, and then the green function, when we're less than 2, we follow x squared. So of course you could plug in some values. 0 squared would be 0, so it passes through the origin, and at 1 it would equal 1, so we have a spot there, and of course at 2 it equals 4, which we know is continuous. So we have a graph that goes out like this, and it is not, just by looking at the graph, it is not differentiable because it's not smooth. There's not a smooth transition in the derivatives. So we have, the derivative there is negative, it's negative there, it's equal to 0 there. It's increasing, 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 and then it just flattens out. So even though it's not a pronounced sharp turn, it's not differentiable there. Okay, let's prove it algebraically, and let's do the green one over here on the left. And so we're going to use the limit definition. Give myself some more room. We're going to use the limit definition. So the limit as x approaches 2 and x minus 2 on the bottom. It's just the difference quotient, or the slope, and it is f of x minus the function value at 2, which we already know is equal to 4, right? So we have x squared minus 4 over x minus 2, and all the while it's the limit as x approaches 2. And of course we could factor the top out, get x plus 2 and x minus 2. And on the bottom, of course, we have our x minus 2, and so we're able to cancel that. And now we just left with the limit as x approaches 2 of x plus 2. And what do we plug in? We plug in our 2, and we get 2 plus 2 is equal to 4. Alright, so now let's take a look at the red case over here. So still we're using the same limit value, the limit as x approaches 2, and it's x minus 2 over the function 2x minus the function value at 2, and of course we have 2x minus 4. We already knew that it was continuous at this spot right here, and then we have x minus 2, and once again we're still looking at the limit as it approaches 2, and then of course what can we factor here? Looking at the numerator, we can see that they both have a 2 in common, so we're going to factor the 2 out. Whoops. Let me get rid of that. We're going to factor the 2 out. and we're left with x minus 2, and we have x minus 2 on the bottom, which we have cancellation there, and so the derivative is equal to 2. And since the derivatives at 2, they don't match for this piecewise function, you can see these two don't match up, so therefore it is not differentiable even though it's continuous at x equals 2. So it's very similar to the limit definition of continuity, except for now we're talking about the derivative's continuity, if you will. So anyway, hope this helps out, and when you're working on your homework this evening.